So, esteemed colleagues, well, the topic at hand, it has been clearly articulated here. And indeed, you know, I am speaking under the very banner that I consistently and passionately advocate for all the time. The main focus of our seminar is not to delve deeply into a detailed analysis of past events in the field of linear physics. No, no, no. There are plenty of other seminars out there, yes, where they discuss similar, you know, ether-like, those very kinds of topics. There are many interesting subjects, but I believe our main topic, after all, is indeed cold fusion, linear, that is to say, and those pioneering works being carried out in this field, and it would be a shame not to know about them and to share one's perspective. All right, so, well, I'll begin by telling you that right now there is this new Fire Energy website, and I am constantly receiving their newsletter. So it's likely that others can also receive this kind of newsletter. So either with my assistance or Tsvetkov might be able to help. Well, just take a look at this. So the most recent message, it was about January 20th. But wait, January 20th? When exactly was that? All right, so let's talk about it. It was yesterday. So then the generator, it's called E Cat NGU. What NGU stands for, I don't know, but let's just keep that abbreviation for now. So here's the thing, by the way, in this particular message, I'll be elaborating on its full content a little further on. It's clearly and unequivocally stated that supposedly there's absolutely no linear involved here, folks. What we have here is a completely new method for generating electrical energy. Look for physics elsewhere. The focus is on what's called, well, the main word, the core message, the main term, so to speak. It's these coherent cluster electrons. And so the scheme there, which involves patents, based on which you see the commercialization of this device finally begins, is presented on this very same website, and you can independently look at this patent. So it's presented right here. Actually, the most interesting and indeed the most important thing is, this upper diagram. Now, what exactly do we see here? Well, it's quite clear that there's a plus-minus connection here on the left-hand side. This, you see, is the primary source that's powering this particular diode. Well, you can't see any letters, nothing here. It's poor, unfortunately, but that's how it is on the website. So it's just a low-quality image. So look, this right here, this thing in the right-hand corner, this square-like shape with a small circle, and then with these two components, the anode and cathode, this is what we call a diode, a vacuum diode. Rossi was the one who named it. Next to it, you see, in this box, there's another thicker square. That's a magnet. So the magnetic field is directed along the current. Pay attention. And it says so in the text. Well, then, the third important detail to consider is that right here, positioned in the very center, there is also a storage capacitor, which, generally speaking, is connected to the opposite end of the cathode. Now, the triode here, as Rossi himself asserts, is, one might say, a desirable component, but it is not strictly necessary. The essential component, the one that's really needed, is this diode right here, where Volodya Chepelev and I, we were, pondering and pondering for quite some time, because with a diode and a power supply drawn in this manner, the circuit simply shouldn't function. So apparently there's some kind of error here. Well, let's assume that the error is insignificant. So the circuit works, and ultimately the diode allows current to pass in one direction, and in the other direction it, so to speak, blocks it. So Rossi himself emphasizes that, well, I need to consider this specific load. This, in the top left corner, is the load from which he extracts electrical energy or thermal. I don't know. It doesn't really say much about that. It's important that in this load additional electrical energy is captured as claimed. You can, so to speak, primarily draw electrical energy. All right, well, we'll definitely be returning to the triode. Its role, is actually quite significant, among other things. So you see, the circuit itself is really quite elementary. What's there to even elaborate on? So the capacitor, it charges up first and foremost. That's the main thing. Initially, until it fully charges up completely, there's absolutely no breakdown. And then once it's finally charged, boom. So this diode must break down and current will flow through it. So at the moment of breakdown, as I'll show later, this is my circuit. I designed it, you see, for a gas reactor and a water reactor. This is, you could say, a circuit for reactive oscillations. So the capacitor charges, then it quickly discharges. So oscillations arise. And these oscillations, so to speak, they are indeed present. So what forms then is a plasma layer and also a plasma column, right? Although Rossi claims that he has a vacuum diode. And here questions start to arise. So these very oscillations, if you were to filter them out, it's understandable that some of them, which are directed along the current, they can potentially amplify this current, while those that are against the current, they get filtered out. And so now here is the content of the patent. Now, this is the very electrical diode. I've already told you about it, so here it is. What we have here, pause, this is an electrical diode, a vacuum diode, pause, and then right here we have the second position, pause, a vacuum diode, specifically with electrodes, you see, pause. Now, as for the check valve, that's the electrical diode that was up there at the top. So, it's important, as this Rossi says, even though I don't fully agree with him, it's important to have a shirt around. So generally, its electrodes are, well, pins. Well, I was looking at a picture, I came across it somewhere, and they are cylindrical pins, or rather cylindrical rods, on which essentially you have. It's in a cup made of, as he describes it, a titanium-based ceramic, which he explains contains both strontium and nickel. But then he goes on to say that it could actually be a ceramic based on barium titanate alloyed with either nickel or strontium. That's what ceramic is. Well, barium titanate, as is well known, possesses extremely strong piezoelectric effects and is therefore utilized in piezoelectric sensors. So if any acoustics or electrical oscillations arise there, it can indeed somehow interfere with the operation of this vacuum diode. Magnet. So what's the purpose of the magnet? Well, Rossi himself claims that it is supposedly oriented along something. And this is quite well known. If it's longitudinal, then in lasers, this kind of system is used to, well, facilitate the contraction of the discharge, to narrow its cross-section, that is, to increase the current density within the discharge. So it's important for him to form an electron beam that doesn't spread out, hitting the walls, but instead reaches the second pin of the anode. So this was the scanned one, you see. But again, I'll have some questions about that. You'll see more about it later on. So what does all of this mean then? What kind of magnet? So for each position, it means, well, the keyword is, here's the magnet at this specific operating mode, which it carefully selects by increasing, and all its regime parameters, meaning the conditions under which its entire setup functions. Next, I will now elaborate on these particular parameters. It significantly increases the coherence of electrons. Well, guys, this is a powerful statement that needs to be verified. It directs the flow of electrons into a narrow, powerful beam. Well, I mentioned that. So now here, well, it is being claimed that it is responsible for generating an internal flow of electrons. This stream of of coherent electrons. He also says that since these are pulsating bunches, it must be a system that truly can excite electromagnetic oscillations. This, so to speak, is no different from a conventional magnet transformer to pulse, but it's very important to him, you see. He says in there, I did, after all, learn to make this coherent electron beam. There, the electrons are, as a rule, phased. That's what he's talking about. So what we were just saying, phased electrons, this primarily means they have a collective nature. That is, they interact with each other and act as one single electron. It is widely claimed that there is no dependence on high temperature synthesis, or that no transmutation of chemical elements occurs there.
Total. This is Zatelepin speaking. But perhaps after all, a little more detail. You'll explain. Wait, I haven't asked the question yet. Using some physical terms already. What is meant here by the term coherent electron beam? What is that? Not in general terms, but more precisely, how?
Well,
if possible.
What exactly does each and every single electron truly signify? How, I mean, from the fundamental point of view of...
Is this a quantum mechanical property, or is it some other kind of thing?
This is a quantum mechanical property in which that is to say, its de Broglie wavelengths are phased. So in this respect, not only do they become, so to speak, a single speed, but what's important is that they even have the same initial phase. So somehow it's possible to form the front of this de Broglie wavelength phase. There.
The answer has been received. However, we still need to explain how the de Broglie wavelength is measured.
Wait, I will definitely proceed to tell you everything that I have managed to figure out and come to understand.
Come on.
So he says a few words about how the power supply is constructed. In general, I've already spoken about the cathode arm and the anode arm. And as for the magnet, so to speak, I mentioned it again. This was taken directly from the patent itself. I was simply translating. Here you can read for yourselves exactly what he says. All right, then. And then so the very last one we have here is the vacuum triode. What exactly is its function? In fact, these benchmarks, these electromagnetic oscillations, he is capable of convert not only either it oscillates on its own, or this triode is amplified, and then the cathode ray already begins to contain. It explicitly states clusters there, not just coherent ones, but clusters of coherent electrons. This is what the particular set of sounds, which is detailed in the description of this patent, signifies. So just a second, I'll try. This way will be better for me. So now what I mean to say is this particular thing, it's described here then that this pulsating current goes into the load and is detected, right? Well, the most important thing is what he's saying, which is a few words about this particular shell that surrounds the anode and cathode. He says that they are built directly, he states, on the basis of barium titanate or strontium titanate. There. Now it says the very same thing. This is, after all, it's a truly important value that allows us to make certain estimations. So this is the exact field strength that should be present within the magnet. It clearly states 2 Tesla. Well, I'll explain to you what 2 Tesla means from the perspective of an experimentalist, as I understand it in terms of plasma processes, because I have worked with such magnets and also used them for the collimation, of plasma beams, so to speak, and I use them for arcs and for glow discharges as well. It is precisely at 1 Tesla that a very strong impact begins to be exerted on the electronic components. They start, so to speak, to truly to contract. Magnetization is obtained, so to speak, under those conditions, under which perhaps the Tesla generator operates. So I will now elaborate below on what conditions. What this means is that the magnetization here is not of ions, but only of electrons. And it's achieved with such a field. Right, now then look. Ultimately, he lets slip just what the exact frequency of these oscillations should be, the ones that he has there, generated by those electron bunches, so to speak, or perhaps by these other specific elements. Piezoceramics, well, it doesn't matter what actually modulates this electron beam. So what does it need for the generator? He precisely states the frequency from several thousand, that is kilohertz, up to several 100 million. This is, it's a range that goes from, let's say, 1 kilohertz all the way up to 100 megahertz. Yes, from kilohertz to 100 megahertz. To make it perfectly clear for everyone, this is the actual working frequency range. That's it. Here's the thing. Now, Jutta, it's also important to note what I mean. I'm repeating myself here again, but he, in fact, already writes quite differently, you could say, in various sections. Here he's already writing not kilohertz, but pay attention, several megahertz up to 200 megahertz. Well, to change things like that in one and the very same pattern, so to speak, it means the magnitude, the range, so to speak, well, by several orders. Well, it's not very, I think, accurately written, right? What's important is, look, the power supply, which, is voltage is supplied to the main and vacuum diodes. This here is from the electrical main step post, which means its output voltage varies from post 110 up to 300. Quick pause no, 230 volts post. This indicates that the voltage across the diode isn't particularly high. Post, you see?
Tolia, sorry for the interruption. He's asking again. So there's some kind of artificial intelligence module.
This is all just silly stuff.
Is he actually in the picture or not? He wasn't there at all, was he?
And it's not in the drawing. Instead of a triode, he says it's best to use an AI module to put it in place of a triode. But these are all birds of a feather. It's clear that in the end, he lets slip that everything works on a pure diode. Forget about the triode. That's just to better amplify the mode. Ideally, all of this would be a triode, but even better if there were a neural network that could precisely identify the frequency that spontaneously emerges there and then amplify it. That's precisely what he's referring to amplify those chaotic fluctuations within the diode, which simply appear on their own, or to really kickstart them. So, but pay attention, the diode itself has 230 volts, but for the device to operate correctly, and this triode, it really gets this level of electrons going, which then accelerates them. He says that actually the electrons need to be accelerated to the level of 1,000 volts. So kV, ultimately, it accelerates electrons to kV energies. This is important. And now to the questions. I think the presenter will have more questions than I do, but still, it seems to me, well, Rossi, he's a person, so inaccurate. And so, judging by his presentations in Norway, remember, he clearly had plasma there, even though he refers to it as a vacuum diode, but he never actually states anywhere what is the actual pressure inside that vacuum diode. If these are torrs and fractions of a torr, well, I'm sorry, it's still a gas-filled device. A true vacuum device is considered 10 to the minus 8th, 10 to the minus 9th atmospheres. This is, so to speak, deep vacuum. It says nothing about the vacuum itself or the type of gas present there. Well, at least it's known that all metals, meaning metals, are used there. They are always saturated with hydrogen, so to speak. Well, there will always be outgassing. The gases are saturated with this, the atmosphere, the same applies. They are, so to speak, adsorbed. But about diadsorption, about the diode's preparation, he says nothing. And that is very important. So about the discharge parameters of this diode, he doesn't say anything either, but he doesn't mention that he has some frequencies there. Well, he just said thank you, and that's fine. But how? Name at least one characteristic of electric current or voltage. There isn't any. What is the capacity? This is an extremely important measurement. The capacity, this particular value, the capacity, there isn't any. Well, if we're talking about it, he tried in Norway or Sweden. I mean, I've actually forgotten where he gave that demonstration presentation before he really started, you know, the commercialization phase, that whole stage of it. He did measure it there, at least spectroscopically. Remember, he even showed the spectrum and stated the temperature. He said, my plasma reaches 8,000 degrees. That's the thing. But again, it's still unclear what specific temperature he's referring to. At the very least, it would certainly be interesting for us as physicists to know. TE, me, these are the main characteristics. Well, he does specify the frequencies. But what about the duty cycle? What is the duration? What is the pause? This is also extremely important in order to say what the physical mechanism is of this very device that he is using, right? A magnet. Well, again, that's like saying absolutely nothing at all. If this is a magnetic coil, it certainly doesn't speak. From all appearances, this is a permanent magnet, pause. So, but then, what is its geometry, pause? And what about the field's uniformity, pause? Because, as it's depicted in his several drawings, pause, it must have very strong edge effects on the magnet. At the boundary magnets, the plasma is spinning, and boy, how it spins. Inside, it might not rotate. It might just channel itself. But this rotation of the plasma, so to speak, with such fields, I assure you it will always be in non-uniform fields at the edge effects. So, what, or is this nonsense, or is it that, so to speak, after all, so to speak, the magnitude, so to speak, the geometry isn't very important to him? Question, that's it. He says nothing more. All right, let's say he has a deep vacuum, a super high vacuum, but then again, depending on the speed and on this specific capacitance value, we could enter a state, which means plasma formation once again. This is the explosive emission per month. The formation of cathode spots from which plasma is ejected at high speed, even in ultra-high vacuum, high-frequency devices. And it's on these principles that all this electron in electron accelerators and others, they are designed, and these very vacuum diodes are being built to be reduced. So it says nothing about spots that should or shouldn't be observed, right? Well, actually, they can be observed, but erosion can also be observed. And for that, well, it's quite clear then, to completely dismiss Leonard's theory, we absolutely must conduct, at the very least, after this device has operated, an EDS spectroscopy of the cathode material in order to definitively state that Leonard's theory simply doesn't work. That's it, everyone. Just forget about Leonard. Or it works. Because look, if gas is adsorbed hydrogen and you say nickel is present, but why nickel and not something else? They used hydrogen plus nickel. Well, that's definitely Leonard. And then he talks about the extraction of electrical energy. But any lamp, any diode, he doesn't actually specify what the average power output is. Although, in my opinion, the minimum power output that he's going to be selling now is from 100 to 500 watts. His product line is actually rated for up to a megawatt, right? And essentially a power plant is built there. using his components, but then, excuse me, you need to dissipate the thermal energy to remove it, so to speak. So what exactly is a heat exchanger and how much energy do they consume? Not as electricity, but as heat. So regarding this specific load resistance, there's absolutely zero information. That's it.
Well,
this is the initial segment, which I believe serves as an introductory foundation that all subsequent parts will build upon. And now, purely my own perspective on this particular device, based on what I know, I will be making comparisons with my own instruments, specifically the reactors that have been given the abbreviation Plasma Vortex Reactor, or PVR. And the groundwork that was achieved in plasma aerodynamics, I believe, is the most important aspect, though not for our discussion today. What I would like to say is this. All of this, perhaps, could just be a mere deception. But there are important moments for which I personally take full responsibility, and which, it seems to me, truly form a bridge between Russia and myself, a connection that is, well, more scientific. And I certainly don't mean to imply that the words he is speaking are, shall we say, completely and utterly full of absurdity. On the contrary, I believe we are somehow underestimating him. He has, so to speak, a certain unique quality about him. I'm going to discuss this particular point right now. First and foremost, what I truly wanted to convey, esteemed colleagues, is that, well, the absolute most crucial aspect regarding these plasma reactors, and so in conditions of heterogeneous plasma, when the cathode material from the erosive plasma is ejected, you see there's an abundance of heterophase present. That is to say, this charged heterophase consists of, if you will, microdroplets and nanoclusters, which, so to speak, carry an electrical charge. So electric current, you see, even that of ions, is actually, as it's generally known in physics, divided into two distinct types, convection current and conduction current. But in flows, the convection current within heterogeneous plasma, in that region, you'll primarily find an ion-ion plasma. And the electrons, they tend to attach themselves very rapidly. So this convection current possesses a whole array of distinct characteristics. And do you know what those are? It's one of those things, you know, that everyone seems to be aware of, but nobody truly reflects on it as they should. So just look at this. Well, let's say, for example, some kind of ball or elder pith, which you always find for some reason in explanations about convection currents. Let's charge these very elder pith balls and then start moving them at a certain speed. Let's put them on some kind of conveyor belt, and we'll move them at a velocity v, so charges are moving, which means there's a current, there's a magnetic field, and we can tell exactly which direction it's pointing. And now look, I will start running and try to catch up to this, so to speak, conveyor. In the end, my magnetic field is always directed, yes, until I match the speed of the conveyor, this very conveyor. After the very moment I start to move at a faster pace, my magnetic field, you see, it completely reverses its polarity. Just observe, it's now going in the opposite direction. So, what will happen to the pointing vector, so to speak? It was, moving in one direction, and now I've overtaken it. So what happened, so to speak? Did it turn the other way, or what? So actually, these kinds of paradoxes connected with heterogeneous plasma were already demonstrated by academician Avramenko. He was my teacher with whom I worked. I'll tell you about his experiments at some point. In one part of the LCP circuit branch, he would charge a capacitor, then discharge it through an inductor, and he had two spark gaps. So one was simply a plasma type, while the second operated on a heterophase principle. This was precisely the erosive plasmatron that he had proposed. And he was able to switch on both the first spark gap and the second one. And what was it that we actually observed? What resulted? There were decaying oscillations. However, as this oscillation gradually decays, as many of you know, peaks appear at the moments of maximum tension. So it turns out that when you install a heteroplasmic generator, the sine wave doesn't obey the law. For example, I change the source's polarity. The sine wave is damped. It changes its sign, just like a battery's polarity reverses. And these little chips, they are unidirectional. Ohm's law does not apply to them. He always, even in Iftania, he would come to us. A respected, so to speak, commission would gather there at the directors, all the scientists. It was such a gathering, a real get-together at, our director. And so he brought this device, he showed it, and he said, guys, explain one simple thing. I mean, these convection currents, they are at play. They are quite different from conduction currents. These conduction currents, just try to catch them. So, well, it's known that the velocities there are determined by Fermi energy, and that's hundreds of kilometers per second. But here, perhaps they're quite small, maybe just 100 meters per second, and then everything will proceed entirely differently. I will then show how all of this is actually used in real-world conditions for the extraction of electrical energy, specifically in the Lennard generator, how it can be applied. But further on, no matter how you look at it, for us to even attempt to explain the Rossi generator, we will inevitably need to recall the concept of cathode spots and also unipolar arcs. All right, and the very last point, perhaps, that I want to emphasize is that this is still an extremely important aspect, specifically what has been achieved within the field of plasma aerodynamics. This is, for example, if you have a weakly ionized non-equilibrium plasma and I send a shock wave, then, what happened was everyone believed, if you were to open Razor's book, you'd find it there. But it was Zeldovich who first demonstrated that at the front of a shock wave, a potential jump arises, and its magnitude is determined by the electron temperature due to the fact that fast electrons move ahead of the shock wave front. The ions cannot escape, they are being compressed. And here a formula is presented, which indicates that this particular jump cannot exceed a certain limit. And at 1 electron volt, it typically falls within the range of 1 to 10 electron volts. But in heterogeneous plasma, it was first discovered that such a spike, you see, can reach hundreds and sometimes even tens of kilovolts. And now I will demonstrate what this phenomenon leads to from the perspective of the Rossi generator. So, just a few words on the cathode spot. You all know well what the cathode spot is. It's a mystery. It's still largely unexplained, especially its movement against the Lorentz force. It doesn't follow Lorentz's law. Electrons, for instance, follow Lorentz, but this one goes the other way. Why? But the most important thing is what develops there is quite significant erosion. So the spot itself, as it is currently understood, is formed on the cathode surface. This phenomenon is primarily caused by the impact of ions. Essentially, it's a process of ion bombardment. Consequently, this results in secondary electron emission. However, it's important to note that beyond this secondary electron emission, plasma is also ejected and emitted from this very location. So the plasma ejected from the cathode spot, it can reach, even in a corona discharge, and many people aren't aware of this, very high speeds, ranging from 1 to 100 kilometers per second. And the velocity reaching 100 kilometers per second is something that can only be achieved in a vacuum. The lower the pressure, the greater this particular speed of the plasma torch becomes. So, the latest experiments are now intensively conducting research on the irradiation of the tokamak's first wall with helium streams. I always talk about this, and I will never stop talking about it, you see, because, well, the flow is uniform, but the surface damage, you see, It depends on the concentration and on the magnitude of the flow of these helium particles, of helium ions, and it depends on the preliminary heating of this tungsten or, some other material. But as a rule, everything is currently made based on tungsten, the first wall of the tokamak. So if you heat it to 1,000 degrees, you'll already see grooves. But note this. It only takes 30 electron volts for such grooves to appear. At 1 electron volt, they're practically invisible. I'd like to remind you that typical cathode voltage drops can actually reach values of up to 300 electron volts, just to give you an idea of the order of magnitude involved. This is a very important point that we must note, that in this very Rossi diode, I assert there will always be present not only electron flows, but also erosive plasma streams. So what will this lead to? I'll show you more in a moment. Now here's the second important result that we will need. This is for explaining the operation of Rossi's reactor and also my own reactor. This is, well, the effect of the so-called gas plasma detector has been discovered within a gas flow. If you take a setup like this, for instance, on a plate, you have an anode and a cathode, and here there's a gas flow, let's say, of air. What we found is that when there's no flow, the current, I'm applying a sinusoidal one, for example. Oh, excuse me. So, well, let's just take, for example, 50 hertz directly from the mains. So in my case, the current is actually maintained, it's not interrupted, and the voltage always, as a rule, forms these shelves. Where you see the shelves, that's the voltage. So this is a typical AC discharge, meaning an alternating current discharge without flow. In the flow, everything is constantly changing. So then, well, it's quite clear that from the anode, ions will move here, and from the cathode, electrons. So, but, well, this is then in just one particular case. And if I were to change the polarity, then the ions would be forced to move against the current, and specifically within the boundary layer, which means they'd have to move directly against the flow. It would seem that for such a tiny particle, there shouldn't really be any significant resistance force, because it's a Knudsen regime of collisions. So, nevertheless, it actually turns out that it's quite possible to just blow away these specific ions, and for that, you really don't need a whole lot, just, the flow rate, so to speak. It's enough to have, say, 100 meters per second. That's already a real speed, which will be sufficient for them to move freely in one direction and slow down in the other. And it gets to the point that I can actually stop them in one direction, as shown here. It's working normally. The tension is pulsating very, very strongly. Please pay close attention to this. And here within the flow, it truly begins to get agitated. So in the latter part of the period, this can be achieved, but it continuously diminishes. This peak of the current keeps getting smaller. This means it's not throughout the entire duration of the period. One can reach a point where it won't flow whatsoever. Satana Soto, a typical diode pattern emerges. This means you get just these half-period current and voltage pulses. So now let's move on to So to the generator and my PVR, I'll show you later, and cross. So he charged this capacitor. Then the discharge starts. Well, that's fine if it's a small capacitor. But what if it's a large one? Like, what do I mean by small or large? I'll show you now. A mere 1/10 of a microfarad is already quite sufficient for, so to speak, a cathode spot to form right here. You see, this isn't an explosion of the cathode, but rather it's intense heating, and from that point, the detachment, the formation of plasma begins, and the cathode starts to overheat. From this location, as is always the situation, either an acoustic wave or a powerful shock wave begins to emanate. Always. Even a corona discharge will whistle if you listen closely to it. It whistles, it's always active, meaning this phenomenon then, due to the energy release zone, a plasma piston is generated. It works to accelerate this residual gas, so there you have it. And what is it that we say? What that means is the shock wave itself, generally speaking, well, it's really just the same wind, which can, in fact, so to speak, slow down the ions that are provided or needed. And so at this point, everything already depends on the geometry of this particular diode or this particular reactor, which means you can find the resonance for this acoustic standing wave. And even in a single pass mode, even in a single pass, you will always have this asymmetry of current flow. A small current will flow against the wave, and a large current will flow along the wave. This is something we must know in order to ultimately get closer to comprehending the operation of the Rossi generator. But now, let's say a few words about what's actually taking place at the forefront of the shockwave. For me, this is my daily bread, but for you, it's completely new material. However, it's a known fact that, for instance, when a shockwave explodes in mines that are completely full of coal dust, two distinct shockwave fronts emerge. The first one travels along, you see, it compresses, the air, a methane explosion occurs. Well, let's suppose then that one compresses the air and the second one compresses the dust. And the distances between these fronts can be very, very large. So actual calculations show that, if we take, a two-component system in which all in all, the mass ratio of some ions, let's say, is 32, and of other ions,
Just a moment, please. I apologize, my phone was ringing.
So then the second group is 65. All in all, that's 66, just about twice as many. So these are the actual profiles, calculated to be precisely like this. So if one set is, negatively charged and the other set is positively charged, then what we get is, charge separation. How does that happen? It's due to the fact that more massive projectiles, they possess the inertia of more massive particles. Accelerating them is considerably more challenging than accelerating lighter particles. Pause. So, in essence, this device functions like a Van de Graaff generator where we mechanically separate these electrical charges. Pause. The calculated magnitude of the electric field here, it can actually reach values of tens of kilovolts. And so, at this distance, which in principle, this xk lambda might not even be that large, just a dozen mean free paths difference in total. But it turns out to be tens of kilovolts. And what's the outcome? And as a result, at the shock wave front, for the first time, I want to stress your attention. We gained the ability to create a charged particle accelerator and electrons, even more so, charged ions at ultra small distances on the order of the length, so to speak, essentially of unimpeded movement. What this means is an accelerator like this one can provide you with the acceleration of ions up to kilo-electron-volt energies. No one knows or talks about this. I told you. And please remember, this is a fact that we discovered in plasma aerodynamics and which, in essence, allowed us to control flows, to achieve a breakthrough, towards creating flying saucers. Right. So what's the point of all this then? What exactly is it that I'm trying to say here? That, well, if we're talking about this being a characteristic, mean free path there for smaller ions, it was 60. Well, let's just say, for example, we take the average for air ions. So it can reach very small values, meaning down to 10 to the -4 centimeter. If we're talking about plasma that can be heated to 1,000 degrees, for example, a typical one I took at atmospheric pressure. So for charged clusters, the size of this particular accelerator will be substantially larger, amounting to fractions of a centimeter or even tens of centimeters. But these are still miniature devices. So if this is possible, then just imagine such an accelerator approaching a nickel target, where, so to speak, all of this is created within a hydrogen plasma. Well then, Leonard, you see, you already have these keV protons accelerated by a shock wave. So perhaps there's no need to search for Leonard's enigma. I mean, in principle, if you take plasma, and you take nickel cathodes, so to speak, and you create a modulation, an acoustic one, or, you create a shockwave generator, that's it. There's nothing else you need in the reactor, really. Perhaps people are indeed following this path, but by some roundabout ways, so to speak. After all, it's enough to have an electron or proton accelerator, and there are plenty of those, so to speak, in Czechia and in Poland. All they're doing is this. So it employs giant-sized proton accelerators, on a glowing discharge, so to speak, for the purpose of studying the process. Well, that is LENAR there. This is an important preparation, but it allowed us, you see, the bow shock wave. You see heterogeneous plasma. So we changed the fields there. These I was talking about. We changed the polarity. We even used a DC discharge. And thanks to these, accelerated streams of charged particles, essentially, all of this was influencing the surrounding atmosphere of these flying bodies, ultimately leading to quite significant effects, to a transformation. Here we see the measurement of resistance change by tens of percent, and sometimes we even reach 80%. So by employing this specific type of heterogeneous plasma in actual aerodynamic experiments in wind tunnels, which, so to speak, demonstrate just how significant the role of this convective current truly is and how crucial the presence of this leading shock wave proves to be, which yields the maximum effect. This was something we observed at supersonic speeds and even more effectively at hypersonic speeds. So, and this is a direct verification of this particular tenet of Biturin's and Belocon's theory. Well, I just tagged along Klimova, you see. So we wanted to create a physical BBK mechanism. Here, an experiment is shown in a shock tube in which this cluster plasma is created, and this pinkish beam, which was fired from the Avramenko generator. Essentially, this is a capillary discharge where 100 amp current was evaporating the hydrocarbon wall, by the way. So with the nickel electrodes, we were able to obtain the maximum results. So then this kind of plasma beam was produced, a collinear beam, which did not diverge. Well, it appears that in this plasma, it is necessary to thoroughly investigate both the surface tension, something of that nature. This was indeed the path towards the creation of an artificial ball lightning phenomenon. And towards this very beam, a formed shock tube was directed, delivering a shock wave with its specified characteristic parameters.
And so in this particular section, specifically within the control group, right here, one probe was positioned and then a second one. So we observed that is the potential within this plasma, how the floating potential changes within this plasma because the plasma itself is quasi-neutral and consequently it was ejected. And it's clearly visible that indeed as the shock wave arrives, a distinct jump appears here and then a second jump appeared on the reflected shock wave. The magnitude of these voltage jumps was anywhere from 300 volts all the way up to a full kilovolt. kV is kilovolts. So what we're looking at here, this is the actual reality. So the thing is, the pressure right here is exactly 42, but under these specific conditions, the impact beyond the front of the shockwave at 900 meters per second, these were already only fractions of an atmosphere. Therefore, it can be considered that even within an atmosphere, such fields can be obtained, and it's not a significant magnitude. But here, I want to emphasize once again that it is precisely this point that is so important, that these potentials were appearing, and as a direct consequence, within these potentials, the electrons were very significantly accelerated. They shot forward, and then the precursors emerged. These plasma precursors, we observed them just a meter before the shockwave's arrival. These were truly vast distances, effectively clearing a path and already influencing the shockwave's parameters. Well, and now we're finally getting very close to the Rossi generator. And to draw a certain connection, so to speak, with my PWR generator. This is one of the best systems that was created in 2013. So what we have here is the vortex generator, which was swirling the gas. And then right here, the anode was ignited by means of a Tesla coil. You can see the cathode right here at the very end. And now you're seeing this footage. I particularly like how these tiny droplets are emitted from the cathode here. And as they hit this streamer, this plasma filament, they light up. So you see one ejected, the other ejected, and a shell forms around them. There it is, there it is. That is, they explode with the formation of a shell of nanoparticles. Then we collected these nanoparticles, these droplets, that's it. And so we would analyze them, we would send them off for analysis, and that's how it was done. Well, this is the process of the actual, so to speak, formation of heterogeneous cluster plasma with enhanced electron erosion of the cathode. And this is something we're not hiding, meaning the mode that is necessary for this reactor to operate. So then, well, the reactor is working, that's clear in the pause. And the working mixture, so to speak, should primarily be hydrocarbon containing, pause. Hydrogen, that is water vapor plus argon, pause, yeah. And for such a generator to function, we needed 100 amps of operating current, but there's no such current. So what? We only have 2 amps. Well, you see this circuit here, it's really no different from Rossi's circuits. We have a power supply unit, for instance, not 230 volts, but 7 kilowatts, but it does exist. And this reactive capacitance, which is 680 picofarads, we are not concealing anything at all. A selectable variable inductance, and right here, so to speak, a discharge gap. Yes, a discharge gap. This could be, you might even call it a vacuum diode, because the entire setup itself was tested using a torus, and we observed its operation all the way up to atmospheric pressure of the air. So what is it that we see? Now take a look. This container is currently charging. Right, well, 500 volts, 1 I saw to 1, 2, 3, 4, up to 4 kilowatts. And then a breakdown occurs here. So this capacitor, you can see how much energy is stored here, Cu squared over 2, and then it goes bang. And right here, you see the ignition voltage in the reverse half wave. So there can be several of these. This is in a periodic mode, or there might be several oscillations. And the yellow line, that's how the current began. So it's clear that, thank God, everything's fine. So here's the power that's being dissipated here. The oscilloscope itself integrates it point by point, current by voltage. It appears in red. This is the, what's its name? The power graph. Well, the oscilloscope is still often capable of, over a long period, we can observe up to 10 seconds of the average power that is obtained in this. So we have dedicated a significant amount of our efforts to the creation of this particular type of heterogeneous plasma. And I would like to emphasize that these specific convection currents can indeed be substantially amplified. But we had a problem, you see, how to extract the energy. So we moved from the first reactor to the second, which uses a water vortex. Right here, I'm showing, you see, the vein swirler. And here we have the swirling fluid flow. And then right here, well, yes, inside, a cavitation funnel forms. And this gas, you see, it actually breaks through from the anode, this component here. That is to say, this is the anode. And the cathode over here can be interchanged, you understand? Well, it's quite clear that if right here, within this particular bubble, which, as you can see, is quite visible right here, if plasma forms, then it's obvious that it will be drawn in by this, quite effectively. Convection currents will be, well, not even by wind, but by a much denser medium, so to speak, like water, meaning they will be quite easily carried along. And so when the plasma overheating begins, precisely at the moment of pulse breakdown, right in the cathode region, what we hear then is such a tremendous crackling sound that it's truly frightening to even approach this reactor. Indeed, Valery Nikolaevich himself witnessed how it crackles there. Yes, that's right. There are shock waves. So everything depends on this magnitude, this capacitance. Here, I'll show you now. This is just a high-speed film that shows that the discharge really occurs in the bubble. I have already shown these pictures to you. So here, and the green area you see, that is the erosion, so to speak, of the electrode itself. It is visible that, so to speak, this particular aluminum electrode was positioned here, and it glows with a blue light. Here, the water is decomposing. It's purple here, but it's actually red, and hydrogen is present in large amounts. So, is that all? Let's proceed. But pay attention, this is an important point. We increased the capacitance there to 1/10 of a microfarad. And what do we see? Well, notice it's already failed here. Now the capacitor is charging again. This one here, it has shorted out, the green line you see. That indicates the current. But now please pay close attention to the purple line. Here you can see the voltage, which is positive. Then it goes to 0. So here it's indicated by this yellow line. And then it went down. The voltage is moving quite asymmetrically, meaning the voltage went much further down than it went up. Then again, you see, it went upwards. Well, and here you can clearly see that the downward movement is significantly greater than the upward movement. And the oscilloscope, you see, it doesn't understand anything. It simply multiplies one value by another. And that's what it shows. Look, the power here is currently inverted, but now the power is normal. This right here is positive power, but then sections with negative power start to emerge. Well, so to speak. And what about it? If we consider what the oscilloscope displays, I measured an average power of 110 watts. But if I honestly take the capacitance, C is known, the trigger frequency is known, 12 kilohertz, and how much it charged up to, that's also known. I'm getting 200 watts, but that's double the amount. And when you calculate the specific value, the efficiency, what then? What's the right number? Is it 343, 3.5, or 1.9? And then we started to think, well, this must all be some kind of trick, a dirty setup, a complete scam. So, on the one hand, if these results are truly accurate, then we should definitely use them. Take them and divert them with a diode in the opposite direction, so to speak. How? Just simply drawing electricity? And from a calculation standpoint, to prevent interference, we actually installed the diode and cut it. And then there were no errors. So everything, whether by the CL squared over 2 times frequency or by this,
everything matched perfectly. So that means we can really get the reactor fired up when, pulsations will genuinely begin to manifest themselves within it. So you see, it's clear here that they are 12 by 6, and it's quite possible to make them more frequent. And there's a direct path if you, so to speak, create the appropriate output of this very power to the outside. Right. But something else, something much worse, was actually observed. Now, if you look closely, this particular part is already fine. The tension over there, so to speak, it means...
Tol, you've been speaking for over an hour now. You really need to try and keep it a bit shorter. Well, come on, try to link your stories to what we're all talking about.
Furthermore, these very shock waves that were forming within the cavity, we detected them both hydrophonically and optically. They caused the walls of this bubble to become agitated. And so, there are actually currents, in this water bubble, or rather in this water reactor. There are currents, that are connected, to electrolysis. So then when the capacitor is specifically being charged, there isn't, so to speak, any actual discharge happening. It is still managing to charge up because there are very small minor leaks present, so it continues to charge. So then the current during this specific period, when we had a rather large capacitance established in our system, observed this. Even the conduction currents themselves, they were capable of flowing in the negative direction. This means that these discharge currents are proceeding quite normally, but the currents that are specifically associated with electrolysis, they are going in a different direction, not the one they should be. That is, they are going against the source. Well, here you can clearly see these high-frequency oscillations, which we observed in the current. And so these are the conclusions. So possible general regularities were examined in Rossi reactors and this NGU, and in PWRV or gas water reactors. This was done on the assumption that the physical mechanisms in these two reactor types are caused by erosive plasma flows originating from cathode spots. Convection and conduction currents were investigated in flows of heterogeneous plasma, or that is, acoustic shock disturbances in reactors, which occur at the moment of cathode overheating. We've examined some well-known features concerning cathode spots, gas-filled plasma flows, and the shock wave front in SNP. I specifically highlighted this, telling everyone, guys, please remember this. The detected reverse currents and negative power within the discharge regions of the PVE indicate the potential for obtaining an extraction, a direct extraction of electrical energy in PVE type reactors, and quite possibly this provides a direct explanation for the Rossi generators. I think that's pretty much everything I wanted to say for today.
Thank you, Anatoly Ivanovich. Friends, you could ask him questions now, but we would completely exhaust our entire time limit. So, I suggest we ask Klimov the questions once everyone else has spoken. But I will ask one question anyway. As the host, I'll allow myself this one.
Well, you told us all about plasma very well here. Where does the energy come from? Where do you harness the horse? What is the source of the additional energy? That's the question.
No, but undoubtedly the energy is obtained, and as it were, solely from an additional power source, only from LENR, no other source.
So where is it, this LENR? What exactly is the process? What's happening? What occurs during LENR? What kind of matter transformation takes place?
With LENR, it's primarily clear that, as has been shown in all studies, the transmutation of chemical elements occurs During chemical element transmutation, everything is observed, including streams of fast electrons, which had
All right, you've answered. So you've answered my question. The substance that flew out of the cathode is for you, it transformed into something entirely different, and that's how you get new energy. Tol, thank you.
Friends, it's quite likely that we will have additional questions for Anatoly Ivanovich Klimov. We'll address those questions later once all the speakers have finished their presentations. Thank you, Anatoly Ivanovich. That was a truly impressive presentation. Thank you so very much. Most importantly, he drew our attention to the fact that this very notorious so-called vacuum diode is most likely indeed a diode filled with, erosive plasma. Well, that's quite possible, although there might be some negligible stresses there, but nevertheless, Klimov has shown us today the mechanisms for obtaining these very erosional flows,